Okay. So, looking at this, basically the idea here, stereochemistry and molecular orbitals for all these reactions. So the E2 I have drawn up. And what you see here is this idea of this anti-periplanar relationship between the hydrogen and the leaving group. So 180 degrees apart. The reason it has to be lined up that way is because of where sigma star of this carbon-bromine bond. It's a polar carbon-bromine bond. Sigma star is where electrons are not at. So that lobe is more focused behind the carbon 180 degrees away. Something we saw with Sn2, which we'll look at in a second. Base comes the hydrogen, the sigma bond, the electrons here move into the sigma star of this carbon-bromine bond. And when that happens, this forms the pi bond, and this carbon-sigma bond breaks. Right, so you end up with a brand new pi bond. You get your Br minus. You have your nitrogen with another H there. Right, whatever else is on there. That's why that matters. So now what if we have Sn2? What's this going to look like? So have our nucleophile. I'm just going to do I minus. Where's the sigma star for this carbon-bromine bond? Same as it was in E2. It's 180 degrees away, right? So this iodine is going to need to come from the backside 180 degrees away. As those electrons from the iodine go into sigma star, that breaks the carbon-bromine bond, and it also causes inversion, right? So this is the kind of the stereochemistry molecular orbital picture for Sn2. Now, in this case, I have it drawn. It doesn't go from R to S or S to R, but it still illustrates the point, right? Again, where this sigma star is why E2 has to be anti-periplanar. Where this sigma star is from the leaving group, the carbon leaving group bond, is why Sn2, right, does inversion, right? And this is that anti-periplanar. Right, so the easiest way to draw it. Iodine is on this side, bromine is left, and then that substitution, right? And if these were all four different things, right, we would have gone from R to S, or S to R, whatever it is. So what happens with Sn1 or E1? The first step is the same for both of these. The nucleophile base is not involved in the rate determining step. The first step is leaving group leaves, and that gives you a carbocation. And we just got to remember that carbocations are planar. They're flat, right? So if I were to say, let's say my solvent was this, if it was going to act as a nucleophile in an Sn1 reaction, it could come from the top or it could come from the bottom. And that would give me a racemic mixture. So Sn1, right, can give racemic mixtures. It doesn't have to, but it can. And then E1 is very similar, but instead of doing a substitution, right, we're again just looking for beta hydrogens. So, right, beta hydrogens, beta hydrogens, beta hydrogens, all over the place here. And the solvent just takes one of those. In this case, it doesn't matter because they're all the same. But again, that's the kind of stereochemical molecular picture for Sn1 E1. Right, you form that flat carbocation. Sn1 come from the top or the bottom, so you get racemic mixtures. E1 just looking for beta hydrogens again. But E1's not worried about anti-periplanar. Doesn't matter.